Good evening, everyone. Today I'm here to present my seminar on the topic Advancements in Intravenous Monitoring System. Today we are going to discuss what is intravenous infusion system, its history, why IV infusions are used, its need, um, and components of the existing IV infusion set, its disadvantages. After that, we are going to see some of the existing intravenous monitoring systems and their features, followed by some research papers done on this particular topic. So, moving on to the main content, which is what are IV infusions? According to a website named Healthline, IV means into the vein. Meanwhile, according to Wikipedia, intravenous therapy is a medical technique that administers fluids, medications, and nutrients directly into a person's vein. The intravenous route of administration is commonly used for rehydration or to provide nutrients for those who cannot or will not due to reduced mental states or otherwise consume food or water by mouth. It may also be used to administer medications or other medical therapies such as products or electrolytes to correct electrolyte imbalances. IV medication is often used because it helps control the medication dosing. For instance, in some situations, people must receive medication very quickly. This includes emergencies like a heart attack, stroke, or poisoning. In these instances, taking pills or liquid by mouth may not be fast enough to get these drugs into the bloodstream. IV administration, on the other hand, quickly sends a medication directly into the bloodstream. Other times, medication may need to be given slowly but constantly. IV medication can also be where to can also be a controlled way to give drugs over time. Certain drugs may be given by IV administration because if you took them orally, enzymes in your stomach or liver would break them down. This would prevent the drugs from working well when they are finally sent to your bloodstream. Therefore, these drugs would be much more effective if sent directly into your bloodstream by IV administration. An IV administration is a controlled administration of medication into your bloodstream over time. There are two main methods of IV infusion, which are pump infusion and drip infusion. About the pump infusion, in the United States, a pump infusion is the most common method used. The pump is attached to your IV line and sends medication and a solution, such as a sterile saline, into your catheter in a slow and steady manner. Pumps may be used when the medication dosage must be precise and controlled. Then about the drip infusion. This method uses gravity to deliver a constant amount of medication over a set period of time. With a drip, the medication and solution drip from a bag through a tube and into your catheter. That's all about the introduction part. So moving on to the next part, which is history. IV therapy, as we know, it is barely a century old, but the practice of injecting fluids into a vein has been around since the 1600s. However, due to the lack of modern science and knowledge of the human body, early attempts to deliver IV fluids and drugs were mostly unsuccessful. The devastating effects of both world wars led to a shift in how healthcare professionals used IV therapy to treat patients and save lives. Despite how long the basics have been in practice, the most significant developments In IV treatment, equipments, drugs, and implementations have been taken place within the last 25 years. The late Middle Ages. In 1492, the first documented attempt at IV therapy was performed by a doctor caring for Pope Innocent VIII in Rome. After an apoplectic stroke, the Pope fell into a coma. The doctor gave him an infusion of blood from three young boys by joining them in anastomosis to exchange blood. Unfortunately, all four died. The concept of IV transfusion is absent from history for more than 100 years after. IV began with the science of how to transfuse blood. The first recorded attempt at a blood transfusion using basic IV treatment took place in the 1660s. The experiment was included two unfortunate dogs which was unsuccessful. Later, Sir Christopher Wren created the first successful IV infusion device from a pig's bladder and a quill. In 1658, he was able to infuse a mixture of wine, ale, opium, and liver of antimony into a dog's veins, and the successful experiment was repeated with other infusates. However, the primitive equipment proved to be a problem. Quills were far too flimsy and delicate and could not be easily fixed into blood vessels. Silver was the next choice due to its malleability and firmness. Wren's colleague Richard Lower devised the new instruments and performed the first successful transfusion between animals in 1665. In 1667, Dr. Jean Baptiste Denis performed the first successful animal-to-animal transfusion after transfusing 9 ounces of lamb's blood into a young man. Subsequent transfusions produced the first documented adverse event, and then later adoption of dubious transfusion practices and the resulting deaths led the French Parliament to ban animal-to-animal transfusion in 1668. With no such ban in England at the time, Lower also performed an animal-to-human transfusion. No transfusion records were noted, and Lower set forth to solve the technicalities of the now proven principle. He designed new devices for controlling blood flow and for transfusions. Out of fear of adverse reactions, blood transfusions were prohibited by the English Parliament in 1668 and the Vatican in 1669. Advancements in IV therapy stalled for more than 100 years. In 1796, Dr. Philip, later known as the father of modern surgery, became the first to suggest human-to-human transfusions. Shortly after his proposal, Dr. James Blundell, a British obstetrician, performed a series of human blood transfusions in 1818 for the treatment of postpartum hemorrhage. From 1825 to 1830, Blundell performed 10 transfusions, 5 of which were beneficial. He also invented several revolutionary instruments for performing IV infusions. The cholera outbreaks throughout Europe in the late 19th century propelled the evolution of IV therapy forward. In 1831, Dr. William Brooke realized the large amounts of water and its saline were lost from blood of cholera victims and that the blood must be restored to its natural specific gravity. In 1832, Dr. Thomas Blatter applied O'Shaughnessy's advice. Using a syringe and silver tube, he successfully revived 8 of the 25 patients he treated with IV saline. In the mid 1800s, we saw the development of needles and syringes in 1845. The hollow needle was perfected, followed in 1853 by the development of first practical metal syringe, and the first hypodermic syringe was used in 1855. In the late 1800s, the introduction of anesthesia during surgical procedures paved the way for safer surgery. In the 20th century, and IV fluid administration was gradually adopted in post-operative treatment regimes. While nurses almost always administer IV today, only doctors were permitted to place IVs until 1940, delegating the tasks to trained nurses allowed for faster treatment and played a crucial role in ensuring the health and survival of countless soldiers during World War II. Well, into the 1950s, IVs were commonly delivered through surgically implanted metal needles, which were sharpened by hand, sterilized, and reused. Many physicians will still remember holding these needles up to the light to detect barbs and filling them down by hand. Heavy solutions were commercially made available in 1930s, which paved the way for medications to be delivered by infusion. Plastics changed everything. Doctors began experimenting with plastic tubes to deliver fluids in 1940s, but it wasn't until 1950 Dr. David Massa of the Mayo Clinic in Rochester developed the Rochester plastic needle. Massa's design included a polyvinyl chloride tube over a needle, which could be attached to hub after placement. This was the first modern disposable IV catheter device, making IV therapy safer and more comfortable. The plastic catheter became more commonplace due to the frequency of IV failure, specifically infiltrations. By the 1960s, the use of IV treatment devices became routine in most American hospitals. IV therapy is now one of the most widely used treatments in modern medicine. Healthcare providers can effectively treat patients based on the milestones discovered by the innovators like Sir Wren and Dr. Latta. After 400 years of research, the development of IVs has come a long way. That's all about the history. So, moving on to the next topic, that is why intravenous infusion. When a patient cannot be orally fed, IV infusions are being used to avoid dehydration of essential body liquid content. This is done by injecting a hypodermic needle in a vein and injecting saline from an IV chamber time to time. The next point is based on how the existing IV therapy works. So, about the IV fluid proceeds into the body due to the pressure difference. The IV chamber is always placed at a certain height from the patient's body. This creates a negative pressure between the chamber pressure and the venous pressure, and this allows the smooth flow of the saline into the body. If in case the pressure is reversed, the flow is also reversed. That is, the blood flows back into the IV tubing, leading to clogging of the tube, wastage of blood, and swelling. The other such adverse effects due to this process are infection, permeabilities, infiltration, embolism, electrolyte imbalance, hypothermia, and fluid overload. The most common reasons for receiving IV infusions are replacement of lost fluids and electrolytes, anesthesia for chemotherapy, drugs that the patient cannot receive orally, transfusion of blood or blood plasma during or after surgery, intake of vitamins, minerals, and other trace elements. That's all about the topic. So the next topic is need of monitoring IV infusion. Numerous complications can arise if not monitored properly. Some of them are as follows: heart attack due to air embolism, blood reflux overdosage, and even death. And that's all about the needs. So moving on to the next one, that is the existing IV infusion system. It has the following components, as you can see in the right side. You can see a figure, and in the left side you can see what are those components, and I hope there is no much need for explanation in that. I hope everyone will be clear about it. So if it's okay, we can move on to the next slide. So the next one is disadvantages of the existing system. So the disadvantages are some of the disadvantages are the system needs to be monitored manually, and it requires knowledge and experience to monitor the IV infusion, which is possessed by medical professionals only. No alerting system is available. Need of manually stopping the intravenous infusion flow. So that's all about that topic. So let's discuss about the some of the products that are available in the market, which pretty much covers the disadvantages of the existing of the old IV intravenous therapy system. So the first one is Dripo, the smart infusion monitor. It is a wireless electronic monitor which helps to measure and display the flow rate in gravity infusions and shares the data through a wireless media. So given are some specifications of this system. As you can see, the display type is an OLED, power source is battery, and battery type is lithium polymer. Battery backup is around 27 hours. Accuracy is 99%. That are some of the main things that you should notice. So this is the product that they designed, and they are providing some features, which is first thing, repo runs 20 hours on a single charge, get higher volumetric accuracy with advanced calibration features. Local area RF networks makes repo more reliable compared to Wi-Fi based devices. Repo is compatible with most IV sets available in the market. Smooth flow rate display for precise rate setting. Easy intuitive GUI with rotary dial based control. Get information of remaining time, elapsed time, infused fluid, and remaining fluid. Gets alarm on rate changes, completion, and if there is any blocks found. These are some of the features that this system has. And moving on to the benefits of this product is that it has infusion safety, accuracy, infrastructure cost, which means tripod doesn't need frequent calibration, and high infrastructure is handy and rechargeable. It is easy to use, and it creates infusion charts for you. And repo is costs 1/4 of the normal infusion pump, and it improves patient experience. That's all about this product. So moving on to the next product, that is the Clarity IV Alert Infusion Rate Monitor, and here is some of the specifications that they have provided, which are display type is a 16:2 character LCD display, power supply is 5 volt DC, battery is 3.7 volt, 1150 milliamp lithium ion rechargeable battery, and battery backup is more than 50 hours in a full charge. That's all about the specifications, and let me give a brief introduction before going on to the features. IP Alert is a rate monitor for intravenous infusions. It is an electronic medical device that senses and measures the rate of flow of fluid, or medical or not, of gravity infusions of a patient. It works for all conventional IV sets. That's all about the introduction part of this product. So about the features, displays infused volume and target volume, variable target volume, and low flow alarm. displays approximate rate of infusion, displays total time and estimated time of infusion, sounds alarm on reaching target volume, low power electronics, sounds alarm on zero flow detection, lightweight and easy to use, one step installation, easy to mount on any kind of stand, LED indicators for low battery, alarm and charging, rechargeable lithium ion battery for backup for more than 50 hours on continuous operation. So that's all about the features. This is the product that we are we have dis this is the product that we have discussed about. This is pretty much a simple thing, I guess. Looks handy, and so that's much about a few products that are available in the market. So moving on to the next topic, which would be research papers that are based on in IV monitoring system. The first one is low cost treatment, low cost automatic intravenous fluid control system for medical treatment. Here, the components used are Arduino Mega 2560, 3x4 keypad matrix, Bluetooth module, flow sensor, and servo motor. In the system, an Arduino Mega microcontroller is used, which can also be considered as the system's heart because it directs and specifies the functions of other components. A 3x4 keypad matrix is used for giving the input order of the number of drops. For controlling drop numbers from a distance, an alternative keypad is set up, which is a key mobile app connected to Arduino via Bluetooth module. A flow sensor of model A flow sensor is used for measuring the flow rate and the number of drops. Servo motor is also used for controlling the flow rate. That's all what I have mentioned here. So let me just briefly explain the working of the system. So the system's operational procedure is systematic. So when the device is turned on, the LCD is the first to light. Upon calibrating, the system informs you to give a flow command or drop count on the keypad or app. It checks the monitoring of drops after receiving the command. When a drop is found, the timer starts. The timer ends when the flow rate in drops per minute has been determined. If the flow sensor measurement is observed to be equivalent to the given command, the system will continue and check from the beginning again. The, the servo remains in its fixed 45-degree position. If the sensor reading and the command do not match, the flow rate is checked to see if the above or below the command. So that is pretty much about the working of that particular system. So moving on to the next one it would be a remote drip infusion monitoring system employing Bluetooth. The system is made up of several infusion monitoring devices and a central monitoring computer. Each infusion monitoring device tracks the number of drops, the infusion rate, and the drip rate. These data are sent to the central monitor. The central monitor receives data from several infusion monitoring devices. These data are visually represented on the central monitor. As a result, the developed system can intensively monitor the infusion status of multiple patients at the nurse's station. The components used for the system are as follows: a microcomputer, PIC 18F4525 microchip, two electrodes, two low-pass filters, bandpass filter, a high-pass filter, impedance converter, three amplifiers, envelope detector, and Bluetooth module. So about the working, the infusion monitoring device is made up of two electrodes, a microcomputer, two low-pass filters, a bandpass filter, etc. etc. The microcomputer generates uh, a 20 kHz square wave. It is then converted into a sinusoidal wave by the 20 kHz low pass filter. The converted wave is amplified to 3 volt 3 VPP by the first amplifier and applied to electrode 1. The voltage at electrode 2 is detected by an impedance converter. To remove noise, the detected signal is routed through a 20 kHz band pass filter. The signal that passes through the band pass filter is amplified by second amplifier by 36 dB and can be demodulated by the envelope detector. The envelope detector demodulates the signal that has been modulated by the rise and fall of each infusion drop. Other electrical devices interfere with the demodulated signal and the signal is fed into the 16 Hz low pass filter to remove the noises. The filter output is amplified by third amplifier to 33 dB and digitized in a microcomputer by a 10-bit analog to digital computer. The microcomputer counts drops, calculates the infusion rates, and determines the drip rate. The Bluetooth module sends the detected data using the serial port profile. That's all about the working. So moving on to the third one, it should be smart infusion pump system for the remote management and monitoring of IV drips. Remote monitoring and controlled capabilities are currently lacking in intravenous fluid administration systems. This proposed system is a smart infusion pump system that can manage and monitor IV drip automatically and remotely. This The proposed system has two monitoring systems. The first one is drip chamber monitoring system, and the second one is air bubble or empty bottle detection system. The drip chamber monitoring system. It has the following components, which are laser module and laser sensor module. And about the air bubble or empty bottle detection system, it has the following components, laser diode and LDR module. These are the two things that I have explained a bit before. So about the working, the proposed device was designed in two phases, hardware and software development. The hardware framework entails the development of a drip counter, empty bottle or air bubble detection system, and tube obstruction detection system, while the software module includes data acquisition and a user interface for interactive remote supervision and control of the entire system. The drop counting system developed use, uses a continuous wave 5 milliwatt laser module to emit light with a wavelength of 650 nanometer. A non-modulating laser sensor placed opposite to the emitter detected light passing through the drip chamber. The Arduino Uno R3 and ESP8266 Wi-Fi shield were used to power and control the system. The latter enables the Arduino microcontroller to communicate with the internet and transfer data efficiently for display on a smartphone. When the sensor gets light from the laser module, its output is assumed to be in the high state in this work, since the drip chamber is enveloped between the laser module and the sensor. Counting fluid drops is possible by detecting the sensor's high-low state. Faults would be reported to a medical professional via information sent by the Wi-Fi module if no drip was detected for more than 30 seconds, indicating an empty fluid bottle. This warning is also displayed on board in the form of blue LED lights. The laser diode and LDR module, like the drip chamber monitoring system, were controlled by an Arduino connected to Wi-Fi shield. When the LDR module gets laser light from a laser module, the output logic is high, otherwise the output logic is low. These components were attached to the intravenous administration sets to blind and therefore would notify its users in the presence of air bubbles via red LED and blink application. So that's all about that system. So moving on to the next one, which would be a system to prevent blood backflow in intravenous infusions. The components required are IR sensor, ADC0804 at MEL 89 at 8089C205 microcontroller and a voice module. So how this thing works is that the fluid is delivered from the IV chamber to the patient via a hypodermic needle via the IV tubing. The flow of liquid at the end of IV tubes is monitored using IR sensors. The sensor is designed in such a way that the tube can be accommodated between the sensor's transmitter and receiver. The sensor output is given to an analog to digital converter, based on which a preliminary lookup table was formed for 3 cases. The following cases are being considered: an empty tube, which indicates an air embolism; tube containing liquid; tube with blood. The ADC result then is provided to a microcontroller in which the two ICs are connected. The microcontroller is configured to operate a voice module that alerts the nurse if any of the previously mentioned cases occur. So that's all about this system. So moving on to the next one, which is a warning system based on the RFID technology for running out of injection fluid. This figure shows the setup, how the system is set up in a room. So let's move on to the working part. A ward may have several intravenous drips serving more than one bed, and an RFID reader with one or more antennas communicate with these tags on bags. The middleware allows the control system to use information from tags inside the room to interact with the PC in the nursing station via the network, either wired or wirelessly. Of course, the PC at the nursing station can communicate with the hospital data center as well. When a nurse gets a new bag at the nurse's station, she can register it to have the stock database in the hospital updated. The system will know which patient bed will use this new bag. It is worth nothing uh, that the used bags can be of any type available on the market without being specifically designed and produced for this system, and the tag can be connected at the hospital. That's pretty much about, I think, and that's pretty much about this system. So moving on to the next system, that would be an IoT based IV drip rate controlling and monitoring device. The proposed device is extended to solve the problems and issues associated with the existing drip setup. The proposed system is capable of providing an accurate automated means to caregivers to control fluid administration through IV drips in home as well as clinical ward under limited resource setting. The proposed system consists of three major parts, mainly main device, sensor unit, actuator and actuator system. About the main device, it is the device core and includes the display, the input keys for the user interface in the front end. On the back end, it houses the controller, supporting electronics and a power source to keep the entire system running. Then the sensor unit, an IR sensor is used in this section of the device. It is used to detect fluid motion in the drip set tank and is placed on the infusion set reservoir to detect the flow rate. Actuator mechanism. The device's controlling setup is located here. The actuator applies force to the flow tube in response to feedback from the main device about the level of fluid, causing the system to close and thus ending or releasing the solution flow as required. The proposed system will include mobile as well as web application functions, allowing for flow regulation and monitoring at the nursing station or on a smartphone for a maximum of 200 devices at the same time via IoT. The proposed design is universal because it is designed to fit all shapes and sizes of drip sets. The following functions were included in the proposed device. And dual notification in the form of both light and sound alarms to demonstrate the end of the flow. Automatic device start or stop via smartphone as well as web applications, and the device is rechargeable. So the next system is automated intravenous fluid monitoring system. The given figure shows how this system is Set up. Moving on, and this is the block diagram of this concept, and the monitoring equipment consists of two sensors, one for heartbeat and one for load cell. The heartbeat sensor, which is placed before the Y injection site, detects a voltage change caused by an air embolism. This signal is then transmitted to the monitoring station's controller. When an embolism is detected, an LED glows to indicate its presence and an alarm is initiated at the monitoring station for swift response. The message from the load sensor is the controller's second input. It detects the level of fluid in the IV bag by baying correspondingly at regular intervals, illuminates an LED to indicate a low level of fluid, and sequentially sounds an alarm which when the set point is reached. The time interval is determined by the need of the individual patient. This helps to keep volume infusion rates under control. The nurse station is notified by these two sensors. So that's all about this system. So we can conclude our seminar, and it has been observed that traditional intravenous infusion kit has several disadvantages like reverse blood flow, air embolism, and can cause even death in extreme conditions. There exist several products in the market which are capable of overcoming the disadvantages of the traditional intravenous infusion kit. Research has been done on this for improving the current intravenous monitoring system by implementing different methodologies and components. So these are the references that from which I have collected my data, and that's all about my presentation. I hope it was really beneficial and helped you collect a bit more information about this particular topic. So thank you.